Hello everyone, and welcome to a new module of ResNetLab on True. In this module, we're going to talk about Beyond Bitswap. Beyond Bitswap is a project that we kicked off last year at ResNetLab on True in order to improve file exchange in peer-to-peer networks. So this is the agenda that we're going to follow throughout the presentation. First, we're going to do a brief description of why file exchange in peer-to-peer networks is hard, and we're going to do a quick refresher of Bitswap and Graphsync, the two protocols that we described in the content exchange module from the core modules of ResNetLab on True. Then we're going to deep dive into the Beyond Bitswap project and all of the outcomes and prototypes that we built for the project. And finally, we're going to describe the future work and new lines of research that we are exploring around the Beyond Bitswap project and file exchange in peer-to-peer networks. So by now, everyone should be aware of how hard is file exchange in peer-to-peer networks, because we have to worry about content discovery, content resolution, and content delivery without any central point of coordination. Luckily, we have a gamut of content routing systems helping us in this quest of achieving all of these goals. We have, for instance, trackers, like in the case of BitTorrent, that we can ask for swarms that are storing the content that we're interested in. We have the example of the Web 2.0, where we have the DNS system in order to find out what servers and the address of the servers that are storing the content that we're interested in. And then we have the case of peer-to-peer networks, where we have the DHC as a way as a directory and a way of finding what peers in the network are storing the content that we're interested in. The problem is that all of these content routing systems there's a trade-off in all of these content routing systems, because either they are too centralized, like in the case of the DNS system, which is quite centralized, but it's quite centralized and also quite performant. And then we have examples like the DHT, which is completely decentralized. But the problem is that when a network grows, when we have a lot of peers in the network, making lookup operations may be quite expensive in terms of performance. So that is why Bitswap exists, because in the end, with Bitswap, what we are trying to do is to overcome many of the trade-offs of these content routing systems. If you recall from the content exchange model, Bitswap is a message-oriented block exchange protocol that complements content routing systems to improve exchange and fetching performance in a peer-to-peer network. So Bitswap it leverages content routing subsystems in order to find where the content is, and then it starts requesting the content from the peers that are storing it. In the Beyond Bitswap project, our goal, after studying Bitswap, after studying Graphsync and evaluating their performance and their limitations, the goal that we had in this project was to make content exchange in peer-to-peer networks blazing fast, either improving these protocols or creating new ones. And the outcome so far of the project has been 10 RFCs with improvement ideas and designs to improve the current state of file exchange in peer-to-peer networks and specifically in IPFS. We built an IPFS file exchange testbed so that anyone that comes up with an idea and a new protocol design can benchmark it easily and debug it easily, comparing it with the current state of the art. And finally, we built a set of prototypes in order to evaluate what if the ideas that we were proposing in these RFCs made sense and were improving the current state of Bitswap and the current state of file exchange in IPFS. And before we jump into Beyond Bitswap, let's do a quick refresher of Bitswap and Graphsync. So if you recall from the content exchange model, Bitswap is a message-oriented protocol with 6 different messages. We have 3 request messages. We have a one-half message, which is used for content discovery, and to these one-half messages, peers will answer either with a half if they're storing the block that we're looking for, or with a don't have if they don't have it. Then we have the want block message or the want block request, which is used for actual content exchange. To the want block request, peers can answer either with the actual block that we're looking for or with a don't have if they don't have it. And finally, we have the cancel message, which is a special message that we use to let other peers know that we're not interested in certain content anymore. If you recall also from the content exchange model, when we try to find content using Bitswap, what we try to fetch is a full DAG structure. So the first thing that Bitswap will do is to find the root CID for that DAG structure in order to get the links for the rest of the blocks of the content that comprises the content that we're looking for. So when we trigger a new session, and sessions are used to are parallel streams of content fetch, the first thing that a new session does is to broadcast a one-half message for the root CID. So we can have the root, and from there, all of the blocks and traverse the blocks in the tag structure. So we will send a one-half. What Bitswap does is to send a one-half for the root CID to its neighbors, and neighbors will start answering if they have or not the content. If one of them, like peer B, has the content, the moment we receive this half message, we send a one block right away because we found the content, we did content discovery, and now we do the content exchange. We send a one block message in order to fetch the content. In the meantime, we may be receiving half messages from some other of our neighbors, and we're going to keep these half messages because after we receive the root CID, from there on, we're going to add to our session all of the peers that have answered successfully, because if they have the root CID, it means that potentially they have the rest of the content. And instead of broadcasting and interacting with everyone and all of our neighbors, from now on, we're going to interact exclusively with the ones that answer successfully to the discovery of the root CID. And one of the things that we did, because Bitswap, when it can't find in any of its neighbors the root CID or some other of the blocks, what it does is to leverage a content routing subsystem like the DHT in the case of IPFS in order to find content. So after building in the Beyond Bitswap project, after building our testbed, the early experiment that we did is to compare the performance of Bitswap when it finds and fetches the content from one of our neighbors compared to the performance of having to find out where the content is through the DHT and then request the content from it. And this is what we can see here in this experiment. We had one seeder, so one Bitswap node, which was providing the content, and then a number of leechers, so a number of different nodes trying to fetch this content from the seeder. And what we see here is that for the case of the DHT, the time to fetch, it's reduced the more peers that fetch the content, but it's always less performant than finding the content and fetching the content from one of our neighbors. If we compare these same numbers and we do the same experiments, changing the number of nodes in the network, so the number of total nodes, so we have a seeder and a number of leechers, so changing the number of leechers in the network, we see that finding content and fetching content using Bitswap, because instead of like resorting to the DHT in order to find the content, is always faster, independent of the number of nodes in the network. So what we learned from this is that this is the way that Bitswap accelerates content routing. I mean, we have a low probability of having of finding the block that we are trying to find in one of our neighbors. But with just one DHT lookup, so just finding the root CID, the fact that Bitswap adds the peers to the session means that for the first block, this is our penalty. If we have to find in the DHT, this is the performance that we will have. But once we find this provider for the block, we add this provider to the session, and from there on, it becomes a neighbor. And we're going to have this performance for the rest of the block of the network. And that's why we say that Bitswap accelerates content routing subsistence, because we just have to do one content routing operation in order for Bitswap to establish a connection with this peer and start fetching the content as if it was a neighbor. So this is all for Bitswap. Then we had an alternative way of exchanging content in the IPFS network with Graphsync. Again, if you want to deep dive into Graphsync, go to the content exchange module, because there's a deeper description of this protocol. The differences between Bitswap and Graphsync is that Graphsync is a request response protocol to synchronize graphs across peers. In Graphsync, we use as request IPLD selectors to implicitly request the blocks that we want to download from the other peer. Again, if you want to learn a bit more about IPLD and IPLD selectors, I highly recommend watching the IPLD model from ResNetLab on True. So the other difference that we have, not only we have a difference in the way we fetch content between Bitswap and Graphsync and request content, but also in the capabilities of the protocol, because Graphsync is a one-to-one protocol. This means that we're going to send a request to a peer, and we have to be sure that the peer has the content that we're looking for, because if this is not the case, the request will fail. So Graphsync has no content routing capabilities. When we want to fetch content using Graphsync, what we do is send a request to the peer that we know has the content that we're interested in. So we send an IPLD selector that in the end is a single CID with some additional metadata. And if the other peer has the content, it will open a stream and send all of the blocks one after the other without any additional interaction. So we see the difference. In the case of Bitswap, we had to request content block by block, and we had a back and forth with all of these peers. While in the case of Graphsync, we just send the selector and we start receiving a stream of blocks from the other peer. Of course, Graphsync and Bitswap had limitations, and that's why we kicked off the Beyond Bitswap project. In the case of Bitswap, one of the things that we realized is that it is currently a one-size-fits-all operation for that traversal. So Bitswap deterministically traverses the block, the DAG always in the same way and for every use case. We don't have a way of configuring the protocol according to the client needs or according to the data that we are traversing. So we blindly always traverse the block in the same way. We get the root CID, we inspect the links of the root CID, we see what links we're interested in, and we start traversing the DAG in that way. It's not like in Graphsync where we can implicitly say what blocks we want to download from the other peer. Also, Bitswap does not make use of a priori information from network events when it starts the discovery or from previous interactions with other peers. So every time that we start a broadcast stage, we don't use any additional information, and we have to broadcast to everyone, see who has the content, and we don't know. It's like nothing had happened before and no interactions, and we didn't have interactions with our neighbors. And this could be fixed, because instead of doing these dumb requests where we just broadcast, see who has it, we could either like use selectors in order to find out in a faster way who's storing what content. We could even like have a map of where the content is so that we can split requests and make a more efficient download, multipath download of content. And also, like right now, one half and one blocks, they include as part of the request just a list of the CIDs and the specific blocks that we want to download. We could make Bitswap protocols, and this is something that we are exploring, Bitswap requests smarter by adding metadata, by adding IPLD selectors, or adding additional information to help the other peers make better decisions about how we want to fetch the content, so that we could make Bitswap a more configurable and flexible protocol. And then for the case of Graphsync, the two main limitations is that it's a one-to-one protocol. We don't have the option of having multipath download like in the case of Bitswap. And also there's no content discovery. So we have to either leverage a content routing subsystem off band in order to find who's storing what content, or we just have to blindly trust that the other peer has the content. And this makes Graphsync not suitable for certain use cases. So that's why maybe mixing these two protocols could be a great idea to overcome many of their limitations. And again, the Beyond Bitswap project was the first thing that we tried was to try and overcome some of the limitations of these protocols in order to improve file exchange. For the use of a priori information from Bitswap and by Bitswap from previous events in the network to enhance the protocol so that we could configure the protocol to be a bit smarter. What we did in the Beyond Bitswap project was an RFC and a prototype that we call want inspection, in which what we do is to inspect what others are asking for in the network for the case in which at one moment we want to fetch that specific content that had been requested before, and we have at least a bit of knowledge of where the content may be stored. We'll see in a moment how this works. Then in order to enhance the discovery of content, a few things that we were exploring was, for instance, the use, and this is something that we have in an RFC, but that we haven't prototyped yet, which is the use of IPLD selectors in order to make Bitswap requests more smarter, like the requests in Graphsync, so that instead of having a flat list of CIDs that we're interested in, we can implicitly say the blocks without having to traverse manually the DAG to the other peer by using IPLD selectors. And another thing that we could try in order to improve the discovery of content, and is what we actually prototyped for one of our RFCs, is using a TTL. So using a way of allowing Bitswap requests to jump a few nodes from us. So not only our neighbors, but to jump to a few peers from us. And this prototype, we called it the jumping Bitswap. And finally, it would be great if we can leverage multipath exchanges. There are a few RFCs that what they suggest are ways in which we can leverage as much as possible this multipath download. Because in Bitswap, what we do is first a content discovery in order to find who's storing the content in the network, and then a content exchange. So we could use, for instance, network coding in order to leverage multipath exchange. We could send IPLD selectors to everyone of the content that we're interested in and receive partial responses so that we can make decisions about what streams of content we can start. So mixing a bit Bitswap and Graphsync. And for these, there are a few RFCs in this protocol, in this repository that you can see in the link in the bottom that you can read in order to see what we are suggesting. And finally, Bitswap does have pretty inefficient use of bandwidth in certain cases because we have to do all of this back and forth. And to improve this, we built a prototype in which we added compression to Bitswap, and actually we added compression at a transport layer for all of the protocols that used libp2p. And really briefly, before we jump into explaining all of these prototypes and RFCs that we built for the Beyond Bitswap project, this is the architecture of Bitswap currently. So we have first the protocol interface that is used to interact with other protocols and with the outside world, where we have two operations, a get operation and a put operation. We have the connection manager that orchestrates the exchange of messages with other Bitswap protocols and leverages the network interface in order to exchange these messages. We had the ledger that in the end is just a key value store that stores information about what other peers in the network are looking for, so that if at one point we receive this content in our block store, we can send the block right away to them. And then we had the core of Bitswap, which was the session manager, because like sessions are independent streams of content fetch within the same Bitswap node, and the session manager orchestrates the different sessions and leverage the content routing interface in order to find out content in the network when none of our neighbors have it. And this is the current architecture. And after the Beyond Bitswap project and some of our prototypes, this is how the architecture looks like right now. We added new pieces into the Bitswap protocol architecture. We're going to walk through them one by one, but we see that we now have a relay manager, which is part of the jumping Bitswap. We have a compression layer in the network interface in order to make a more efficient use of bandwidth, and then the peer block registry, which is used to gather information about what other peers in the network have asked for, so that we can use it to make smarter requests. And let's start with compression. The idea of compression came up from the HTTP world. So in HTTP and in the web, we already use compression in order to speed things up. And we were thinking, why aren't we using compression in peer-to-peer networks? And with compression in Bitswap, we managed to save up to we managed to achieve savings in bandwidth of up to 70% according to the specific data structure exchanged. So this is what we tried with compression. We first tried to just compress the blocks, but the problem was that the level of compression that we were achieving wasn't that high. And also because of the implementation of the network interface, we had to stop the protocol every time that we wanted to compress a block before sending it through the channel. So then we said, let's try a full compression strategy, where every single Bitswap message is compressed before being sent. This had better compression ratings, but still there was quite an overhead in the compression and sending of the messages. So that's when we came up with the idea of, at transport level, implementing stream compression, so that every single byte that left our transport layer was compressed. And the advantage of this is that we could put this transport layer below all of the stack and all of the protocols of the Bitswap message, so that we can leverage additional redundancy. And this approach worked great. And that's how we achieved this 70% in bandwidth savings. So after compression, the next thing that we tried is the want inspection prototype that I mentioned above. For this, we added a new piece in the architecture, which is the peer block registry. And with the peer block registry, what we're tracking is what other peers, what other neighbors have been asking for, and other peers in the network have been asking for by inspecting. So we get knowledge about what others are looking for by inspecting the want messages that we receive from them. Briefly, this is how want inspection works. We want to track all of the want messages from other peers so that we know where content, and we can get an idea of where content may be stored. Because if someone have asked for that content with a want request, they potentially will have it the moment that we want to find where it is. So when peer A, for instance, send a want message to peer C, what peer C does in its peer block registry is add for the CID one, the most recent peer that have looked for that content, which is A. If we receive a want CID for peer B, for instance, we see here the peer block registry tracks this and updates its peer block registry to add B as the most recent peer that has received that content. With this information, if at one point peer C wants to find out where CID2 is, and it has in its peer block registry B as the most recent peer, what it will do is that instead of doing this broadcast stage in order to find out where the content is, and then there is one block, what it's going to do is don't use the broadcast stage, and if we have information in the peer block registry for that CID, send a want block right away to the most recent peer in the list. Because if it has the content, it will send it to me right away with just one RTT. So one block to someone that I think it has the content because he had asked for it, and the actual block. So one RTT to find the content, while in the best case of the broadcast stage, we need two RTTs, one for the one block and one for the one half of the content discovery and one half for the one block. What we're trying to do here is to remove the discovery phase if we have knowledge of where the content may be. We did a bunch of tests in our testbed in order to see the performance of this prototype. And what we realized is that our assumptions were correct, and we were saving one RTT for popular content. So in order to simulate popular content, we did a test in which, instead of all of the leechers, all of the peers that were trying to find content, to find the content from a single seed all at the same time, what we did is that these leechers, they tried to find the content and fetch the content in waves. So first, a few peers tried to find the content from the seeder, then another wave, and so on. And what we see is that the more peers that have the content, the faster that we can find it, up to a point where our neighbors has the content, and we will find the content right away. But in the case of the baseline Bitswap implementation, we still need to do these two RTTs of sending a one half and then a one block in order to fetch the content, while with the want inspection improvement prototype, we save this one RTT by just sending a want block to the peer that we know that has it, because we have an entry in the peer block registry with this peer. And this has another interesting consequence, which is that we reduce significantly the number of messages that need to be exchanged, because by removing this broadcast stage in which we send a message to all of our neighbors, we reduce the number of messages, because we just, instead of doing this broadcast message and there's a one block to the one that has it, in this case, we just send a one block. So we are saving a lot of messages. We see that we only improve a bit the number of one blocks because we're sending one blocks, and we may fail. I mean, at one point, we may send a one block to someone that doesn't have the content, but this will be a penalization of just one RTT by sending this first stage. But we see that this prototype not only made us save one RTT for popular content, but also made us achieve savings in the number of messages exchanged. And finally, the last prototype that we implemented was the jumping Bitswap. And in order to implement jumping Bitswap, we added a new module in the architecture, which is the relay manager. And the relay manager is responsible for orchestrating what we call the relay sessions, which are the same as sessions, but on behalf of other peers. So other peers that are trying to look for content through us. And in order to make this jumping Bitswap work, what we did is to add a TTL to Bitswap messages. And this increased the range of discovery. Let's see, instead of using this GIF, let's see step by step how jumping Bitswap works. So right now, in jumping Bitswap, what we add is this TTL. And in the broadcast stage, for instance, when peer A sends a want request to its neighbors, and none of its neighbors has the content, instead of like having to resort to the DHT, what we do is that my neighbors will send me a don't have, and they will trigger a relay session on my behalf because they still have enough TTL in the messages to be forwarded to other nodes. So these peers that are starting a relay session on my behalf will send a want message to its own neighbors with TTL 0, saying that they are the last peers that are allowed to forward the message. According if these peers have the content or not, they will answer to their through the relay session with a don't have and a have. We see that in the case of peer E and has the content, and it tells this to peer D, and peer D forwards this have message to peer A. So peer A, through its session, will operate as if peer D was the one having the content. So it will send a want block with a TTL1. Peer D will identify the relay session that has active with E and will send a want block to peer A. And peer E will send the block, which will be forwarded to peer A through peer D. And then peer A, what it does is just send a cancel message to let everyone know that, that it has found the content and they can stop their relay sessions. So what are the advantages of this prototype? Well, we improve the time to fetch over having to find the content through the DHT. So using jumping Bitswap is faster than having to resort to the DHT and perform a lookup to the DHT if the neighbors, our neighbors for the tutorial that we set up have the content. So we see here the example in order the experiment. In this experiment, what we did is have leechers and the seeder. We didn't allow leechers and seeder to be directly connected, and we had a number of passive nodes which were Bitswap nodes that neither fetch or seed the content but run the protocol, so they were allowed to start relay sessions. And we tested the time to fetch for the case of vanilla Bitswap, the baseline implementation of Bitswap, and also the jumping Bitswap. In the case of the vanilla Bitswap, Bitswap had to always resort to the DHT in order to find the seeder, because it didn't have a way of through its neighbors find where the content was, because its neighbors were always passive nodes. This wasn't the case for the jumping Bitswap, where we could the passive nodes were forwarding through a relay session our request, and we were able to find the seeder through this barrier of passive nodes. And we see here the performance of finding this content using resorting to the DHT in the vanilla Bitswap. The case where we use jumping Bitswap, so with the TTL improvement, and then what we realized is that we were exchanging a lot of messages by using this jumping Bitswap approach, and we could mix the jumping Bitswap with want inspection improvement, because we are sharing a lot of want messages, and we could leverage this information to gather additional information in the peer block registry and make better decisions to find content. And actually, we see that this improvement worked, and we could improve even more the time to fetch by adding the jumping Bitswap with want inspection, because we could populate the peer block registry with more information. The problem, of course, this comes with a trade-off. The fact that we're flooding the network with more want messages means that the number of duplicate blocks and the number of messages that we exchange increases, because now we don't have a way, when we have a session on our behalf in other nodes, we don't have a way of letting the nodes that are a few hops from us know that I found the content and send a cancel message directly to them. And sometimes this cancel message doesn't arrive in the right way, and this means that there are blocks flowing when actually a peer may have found already that block. And this is also a consequence of using symmetric routing, instead of asymmetric routing. Because what I mean by symmetric routing is that right now, when we try to fetch content, the block follows the same path that the request follows. So we see that if our request was sent using this path, we see that we send this path the request. In the case of the DHT, when we find a provider, we establish a connection directly to them. This is not the case in jumping Bitswap. In jumping Bitswap, the block and the requests follow the same path. The blocks follow the same path as the request. So we see that we follow this path, and then the block will follow that same path. And this makes the number of messages to increase a lot. This wouldn't be the case if we used asymmetric routing, so that we just use jumping Bitswap for the discovery of content, and then peer E would create a new connection directly with the peer A, which is interested in the content. And these were all the prototypes that we implemented. Of course, as I've said, these are 3 prototypes from the 10 RFCs that we designed. So you have more RFCs, and if you're interested in building new prototypes, there are a lot of ideas to try and improve these protocols. There are a lot of RFCs ready to be prototyped. One of the things that we want to try, and we didn't have time, is to implement jumping Bitswap with asymmetric routing in order to see if we can control the floating and have a better performance when the network grows, because jumping Bitswap stops being a good option when the network is large, because there are a lot of messages flowing. We want to prototype, and this is something that we may kick off soon, the use of IPLD selectors for Bitswap messages, so that we can do a content discovery of, using IPLD selectors to find out where the content is stored using IPLD selectors, and then start non-overlapping streams of download with different peers according to the content and their answer to our selector. There are some RFCs that explore and that are being discussed to use blocks of arbitrary size according to the application, so that we can fine-tune the exchange of content to the specific application and the specific data that we're exchanging. As I mentioned, the use of network coding or other kind of coding strategies in order to improve the exchange and the multipath download, and a lot more that you can find in the repo. So I highly recommend going to the Beyond Bitswap repo, reading the RFCs and joining the discussion. And this is an open research project, so feel free to join us if you want to explore and research with us file exchange in peer-to-peer networks. This is all for me. If you have any suggestions, questions, or comments, feel free to reach out, and thank you very much.